I can't guarantee you more coherent though.
That's all right. It's an informal affair. So welcome everyone. We're very happy to have Savdeep Sethi talk to us from the University of Chicago. He's very kindly stayed up quite late to give us a talk at something close to a normal hour. So thank you all for making it. Sav was my PhD supervisor 11 years ago, which is, gosh, time flies. So I'm very excited to have him come and talk to us. He's going to tell us about holography and TT bar. So Sav, over to you. Are you sharing your screen? Is that?
Let me, yeah, I'm going to share. Does that screen show up?
Yep.
So actually, this is also, whoops, not that. This is also the first time I'm using Beamer. So a new experience in terms of presentation. Hopefully not a disastrous one. First, let me thank the organizers for their kind invitation. Indeed, I'm going to talk about holography and irrelevant operators today. It's a direction I'm really excited about, and I'm going to try to overview. I want to discuss less about the technical details and more about, why I'm actually excited about it and what seems to be coming out of it. So first, let me start by thanking all my collaborators on TT bar related projects. One of our postdocs, Daniel Brennan, my two students, student and former student, Shikai Chang and Chris Boko, Hongliang Jiang, Emil Martinek, Alessandro Sprangini, and your very own Gabriella. And I'd like to give some special thanks to my former student who's allowed me to use some of his defense slides in preparing the talk. That was very helpful. This picture, by the way, does this cursor show up if I move it around?
Yeah, it does. Yep.
Okay. And please feel free to interrupt, and it's informal, and I'm happy that it's informal. This picture is from Lake Taupo in New Zealand. I've actually never been to Australia, but I've been to New Zealand on one trip, and it was one of the most beautiful sunsets I think I've ever seen. So I keep that picture handy on occasion.
Well, hopefully when our borders open, we can get you out here. So that'd be good.
It would be wonderful at some point to be able to come and visit, and also vice versa, have you guys come visit Chicago.
Yeah.
Perhaps not right now, as we head into winter. Summer will be better. Though bizarrely enough, even though it's December 2nd, it was almost 60 degrees today, which is surprisingly warm. Wow. So here's an outline. Some of this I might skip depending on time. I'm assuming the talk is roughly an hour or so.
Yep, that's perfect.
So we'll start with an introduction about what kinds of questions are interesting and why we might want to think about things beyond local quantum field theory. And then in part two, I'll overview why TT bar itself is interesting, some of its general features, its interplay with supersymmetry, and how flow equations generated by things like TT bar can be used as organizing principles. And in the final part of the talk, I'll discuss the intersection with holography, namely how string theory, and little string theory in particular, seems to strongly suggest we need to study theories like TT bar. So that's roughly the plan of the talk. This final stuff is in its final throes of completion, and I hope it should be out next week. But we still have to kind of make the draft a little more presentable at the moment. Okay, so let me start with an introduction. So if we start by considering the space of quantum field theories. Quantum field theory, as we know, is an incredibly powerful framework. It describes an enormous amount of the physics we see in nature. And perhaps the most famous example is, of course, the Standard Model of particle physics, which, if anything, has been too successful a theory, and it's been very hard to find deviations to give us hints of new physics, at least over the last 30 years or so. But quantum field theory is also very useful in describing many-body physics in condensed matter systems. And certainly, scale-invariant quantum field theory is central to the study of critical phenomena in statistical physics. So it's a powerful unifying framework. Via holography, and specifically holography in spacetimes that asymptote to ADS. So if we think about some spacetime, we're always going to characterize it by its asymptotics. asymptotically Minkowski, asymptotically de Sitter, FLRW, ADS, and so on. But in the ADS setting, via holography, we can use local quantum field theory to even define quantum gravity non-perturbatively. And that's the famous ADS-CFT correspondence. String theory, which describes perturbative quantum gravity in various target spaces and gives rise to correspondences like the ADS-CFT correspondence, is usually also defined in terms of the local quantum field theory, a local conformal field theory of its well sheet. So given the success of this paradigm, we might ask, what more is out there? We might ask, shouldn't we be exploring the space of all quantum field theories? And quantum field theories in some broadly defined sense, things you can get to from a local quantum field theory, where the result itself may not be a local quantum field theory. And a central question we might ask is, do we actually need more than local quantum field theory to describe physical phenomena? So let me just, so this is very broad as an intro. So if I bore a bunch of people, forgive me. So we often consider trajectories in the space of quantum field theories. For example, you might imagine starting with a Lagrangian that defines a quantum field theory and add some local operator to that Lagrangian. And that local operator will produce some flow. It's convenient to classify deformations of a d-dimensional field theory by the dimension of the perturbing operator. Let's call it delta. So if that delta is less than the dimension, you're going to have a relevant operator. You'll have to have some positive mass-like dimension multiplying the operator. If the dimension is equal to the space-time dimension, the operator is marginal. The coefficient will be a dimensionless number. And if the dimension of the operator happens to be bigger than the space-time dimension, it's irrelevant. You'll be dividing by some mass scale. So as an example, if we started with pre-scalar theory, a relevant deformation would be turning on the mass term. A marginal deformation would be rescaling the kinetic term. And an irrelevant deformation would be turning on this higher derivative d phi to the fourth interaction. And here you'd be dividing by something with mass dimension. Or said differently, you multiply something with by something with length dimension. So marginal and relevant deformations are relatively well understood. Relevant operators will generate renormalization group flows when you turn on the operator. And in a conformal field theory, exactly marginal operators generate motion on the conformal manifold. They parameterize the moduli space of the theory. On the other hand, if you add an irrelevant operator in some effective theory below a cutoff lambda, you're doing something weird in the following sense. The irrelevant operator doesn't really matter as you flow down in energy, it becomes irrelevant, hence the name. But as you go up in energy, you are fundamentally changing the theory. You're changing the degrees of freedom that you would use to define the theory. So in general, you can't add an irrelevant operator and uniquely recover some high energy theory. Typically, turning on one operator and you try to flow up an RG flow means you turn on another operator, another operator, another operator, and there's usually no unique point that you could have started from that you can characterize as the ultraviolet definition of the theory. So the irrelevant case is very, very different from marginal and relevant. So you might ask, well, who cares? do I really want to start turning on an irrelevant operator and hunting around for some new structure? But there's a very strong motivation to do this, which is given by holography. So if you want to study gravity in spacetimes like ADS, say ADS-D plus 1, and you look at the spectrum of black holes in such a spacetime, you can see that the entropy of black holes in ADS-D plus 1 scales with energy to some power. It scales with energy to this power, d minus 1 over d. And that's precisely the right scaling of high energy states to match the behavior of a conformal field theory in one less dimension. So it's field theoretic at high energies in ADS. And that's one reason why ADS-CFT sort of works within the context of conventional quantum field theory, because this high energy behavior is not too large. It doesn't grow too fast with energy in terms of the spectrum of black holes. On the other hand, if you look at flat space and you want to understand what could be the holographic definition of flat space, say d plus one dimensional flat space, again, the entropy grows with a power of the energy, but that power is now d minus 1 over d minus 2. And that's too large a growth to be reproduced by a conventional quantum field theory. So you have to have something else. So holography is a very general principle, just based largely on black hole physics. We kind of expect a holographic definition of any theory of quantum gravity in any space-time with reasonable asymptotics. We just don't know what it could be. And here, this growth of black holes is telling us that whatever it is, it's not just a conventional quantum field theory. So we need something else. Okay, so that's motivation for why we might want to explore beyond theories that we understand today, sort of well understand today. So why is TT bar so exciting? Let me start with some of the general features. So the idea is the following. What are we talking about? So TT bar is defined for two-dimensional quantum field theories. And it could be any two-dimensional quantum field theory that has translation invariance. In such a theory, you always have the stress energy tensor, T mu nu, and you could take the determinant of the stress energy tensor in the following way. You could take T mu nu at some point x, T mu nu at some point y, and you could take the limit as the points coincide. Usually, if you have two local operators and you're taking a coincident limit, you should expect singularities. The magic of this particular combination that appears in the determinant is that you don't get singularities. You may get some total derivatives and things, but you're not going to get singularities that are uncontrolled. That would require you to input something about the ultraviolet structure of the theory. So this operator in 2 dimensions is dimension 2. It's the same dimension as the spacetime. So this is some dimension 4 irrelevant operator that you can construct in a 2-dimensional quantum field theory, which is well-defined quantum mechanically. And this was shown by Zomolodchikov in 2004. You can even do this in non-relativistic theories if you like. So there's something very magical about this operator. It always exists, the theory for any theory that has a stress energy tensor, and it's always well-defined quantum mechanically in flat space. So if you add this integrated operator to the action, you'll generate a trajectory in the space of theories described by a flow equation. And it's described by this flow equation. So the way to think about this is, at first order, you add determinant of your unperturbed theory to the action, and then you infinitesimally correct that by the determinant of the perturbed theory, and then you perturb a little bit more, and you perturb a little bit more, and you get a flow. So this T mu nu is now a function of the parameter lambda that you're using for the deformation. Because as soon as you deform at first order, the stress tensor itself changes. So the next deformation takes into account that structure. What is really remarkable about this story is that there is a formula for the energy spectrum, say on the cylinder, that tells you what the deformed energies are going to be in terms of the energies of the undeformed theory. So there's an equation that says, here's your energy in the deformed theory. Its derivative with respect to this parameter lambda is given by quantities on the right-hand side, which in principle can be determined. So the fact that there's an exact way of determining the spectrum of the deformed theory from the undeformed theory is pretty magical. And this equation people might recognize as an Inviscid-Burgers equation. So something you would see in the study of fluid dynamics, say. If you happen to study a C theory, a starting theory that's conformally invariant, because I haven't really said why we use the words TT bar. We just said determinant of the stress tensor. But if your theory is actually conformally invariant, then your T mu nu in 2 dimensions just has 2 components. There's a holomorphic T and there's an anti-holomorphic T bar at leading order. And in this case, this operator determinant T is literally T bar. T is Z, T bar is Z bar. And you can also see that there's no OPE between the two because one's holomorphic, the other's anti-holomorphic, and there is no mixing of these quantities. So T itself has dimension 2, 0. For example, for a free scalar, a free boson, TZZ is holomorphic d phi squared. And so the operator TT bar itself has dimension 2, 2 and is irrelevant. So this equation, this Invictus-Burgers equation, in general, is actually hard to solve. Because if you start with a theory that's not conformal, you'll have energies that have a dependence on, say, the radius of the cylinder that can be very complicated. Even a massive scalar is already reasonably complicated. It's hard to get a closed form expression for the deformed energy in terms of the undeformed one. But if you start with a conformal field theory, you can actually write down a closed form solution for the energy flow. So the energies, I should have written the left and right side more carefully. This is En as a function of lambda in terms of En undeformed. So these are CFT quantities. Pn is the momentum on the circle, which is quantized. R is the radius of the circle. And there's an exact square root formula here. It's a very interesting formula to look at because it has some peculiar features. Well, the first thing we'd expect is if lambda is very, very small, En lambda should just become En. And one can check that that works out nicely. But then the features of this formula depend on the sign of lambda. So if, for example, I chose a deformation parameter that was negative, then you can see that if I go to high energy states, I'm going to get square root of 1 minus something big, and this is going to become complex. So my high energy spectrum is generically going to become complex for lambda negative. On the other hand, if lambda is positive, then this is well behaved at high energies for any positive energy. But if there were any states in the theory with negative energy, and in a conformal field theory, the vacuum, for example, could have negative energy, it usually does have negative energy, then when you make lambda sufficiently big, the vacuum energy will eventually become imaginary. So there is some kind of pathology in both cases. One case looks very pathological, lambda negative, because all the high energy states are typically going to be imaginary or complex. And in the other case, lambda positive, if you make lambda too big, the vacuum will eventually become imaginary, the energy of the vacuum.
And so what is so complex energy? So that I think of that as a state that's unstable, running away somewhere, or?
That's a great question. So I would have said for the lambda positive case, where like the ground state will eventually become imaginary, the energy will become imaginary. There I would have said, yeah, some instability is set in the theory when you try to make lambda too large. The other case where most of the energies are complex, I don't know how you're supposed to make sense of that out of that theory. And it's possible it simply doesn't make sense, but people are very excited about it because one of the two major holographic proposals uses it with a dual theory that's a cutoff ADS. And there you need this kind of wrong sign lambda. In fact, I'm about to introduce this nomenclature. So in a conformal field theory, the ground state energy is minus C over 12R. So you always have this pathology that for what I'll call the good sign, lambda positive, if lambda gets too large, the ground state will eventually become complex. But for a range of lambda, this is all well behaved. I mean, the energy is all real. For the bad sign, where lambda is negative, all the high energy states are automatically complex. And so for that theory, there's no good range of lambda where all the energies would be real. So,
and if any random CFT or like a particularly simple CFT, like free theory.
Sorry, say again. What?
Like so for this formula in the previous slide?
Yeah, this is for any CFT.
This is for any CFT. So what happens if you pick a particularly simple CFT, like a free theory or something?
Good question. Let's take a look at that. Perfect segue to the. Let's make one point before we segue into what happens. So I should say this is a quantum statement too. That's the other beautiful part of this. It's not a statement about any kind of classical physics. It's just an exact energy formula in the quantum theory. But there's something else that's very peculiar about this energy formula, which is the original entropy growth with energy in the CFT was automatically Cardi-like. simply because that's the way CFT energies grow. But here, as you go to very large energies, you can forget the one. This thing becomes square root of that, and the new energy is sort of square root of the original energy, and the growth at high energies is no longer Cardi-like. It's actually going to be Haggerl. So this weird energy formula automatically tells us that this theory cannot be a conventional quantum field theory, simply because it has a Haggerl density of states at high energies. Very interesting, very surprising, and very intriguing. Okay. Oh, we'll come. We're maybe one or two slides from the free example. So let me just make some comments about holography before we get into it in more detail. There are really two attempts at writing down holographic descriptions that involve a TT bar deformed theory as the dual theory. And the first is this bad sign case. I mean, this terminology, bad sign, good sign, kind of, I think people kind of agreed on it as a reasonable terminology in a workshop on TT bar. But this case was proposed as a description of ADS with a radial cutoff. So a cutoff in energy scale set by lambda. It's a really intriguing proposal. It's hard to understand for me at the moment because the field theory side is hard to understand because of all these complex energies. Not quite sure what I'm supposed to do with them. And the gravity side is hard because you have a boundary at finite distance, which means that diffeomorphism invariance has to be modified in some way that's subtle. But there are things that work about it, and that makes it intriguing. And there's been a lot of work on this. In fact, I would say most of the work in holography has been on this proposal so far. There's another proposal by Gibeon, Itzhaki, and Kudasov, which is, so it's good sign, so it has the right sign, but it's not precisely TT bar. So it's something that does come out of string theory, and I'll discuss it more a little bit later in the talk. And it's something that's actually related to what's called little string theory. It is very likely, because it comes out of string theory, that this makes sense. But what we don't really know is what plays the role of TT bar in the dual theory, for reasons I'll explain. So let me, and in explaining those reasons, we will want the following fact, that any theory has a TT bar deformation because any theory has a stress tensor. But if you have a very special theory, like a symmetric product, so this is n copies of the same theory, say, modded by permutations, then you could define something that you might want to call single trace TT bar, which I'm going to call D of X, following notation by David. So TT bar itself would be the sum of the stress tensors for each of these factors, for these n theories, times the sum of each of these factors for T bar. That would be the total stress tensor times the total stress tensor bar. But you could also, in this case, imagine considering the sum of TT bar for each factor separately. And both these theories are solvable in the same way, using this technology that Samolajkov developed. So morally, this second proposal will involve a field theory deformed by something like single trace TT bar. You get the same kind of energy formula out. So that characteristic square root is still there in the second case. And we're going to focus on this second case too, because it really, the fact that it comes out of string theory is really strong evidence that this should exist. I should say the reason this is so exciting is that this is not asymptotically ADS. So we're moving away from asymptotically ADS closer to something that is asymptotically flat. It's not asymptotically flat either, but it's sort of in between. So we're getting there. We're beginning to see what you would need to get something for asymptotically flat space. So,
so these formulas were proved by Kutazov at large N or in general? Like the well-definedness of the single trace and also the energy formulas.
So this you could study all at finite N. And in fact, in this holographic setting, you can in fact study this for each N and see what comes out. Wait, did I misunderstand the question, Gabriella? Or was that?
That's fine.
Yeah. So this just happens to be. I mean, this n will be related to some brain charge in the setup that gives rise to the gravity theory. Like some number of vibrings or something will be this n. But you can study it in every case. In fact, yeah, we'll come back to that when we discuss the holography a little bit more. Okay, so you can go beyond things like TT bar and consider irrelevant deformations, which are products of conserved currents. And those are also very special, and they have many of the same features that TT bar has. And one can try to make sense out of theories of the form TJ bar and JT bar and combinations with TT bar. There's been a lot of work in that direction. We won't need any of that today. Now we can come back to Jock's question about what happens if you start with something like a free scalar, CFT, in 2 dimensions. So here you start with the free scalar, as shown by Teteo and collaborators. You find classically, you can solve the flow equation. So this is not a quantum statement now. The quantum statement is the Zamolodchikov statement about the energies. You could take the energies of the free scalar and you could plug them into that formula. You get the energies of the deformed theory. But here, if you take your free scalar and you turn on TT bar and you solve the classical flow equation, you classically get back what looks like a gauge-fixed non-Bogota action. So you've taken a free scalar and you've gotten back something very reminiscent of string theory.
And so if the flow equation was this Berger's type thing.
Oh no, well, the classical flow equation is this guy right here.
Oh,
so this is
yeah.
It's just a statement that you differentiate with respect to this parameter, and you should get back the operator you've deformed by, which is that of the theory at lambda, that of the stress energy tensor of the theory at lambda.
And this doesn't involve stuff of Zamolodchikov yet, because it's all classical.
This is all classical. This Zamolodchikov derivation doesn't care at all about this. But this is very interesting in its own right. This is a classical statement you can just study in classical physics and see what it teaches you. And it actually teaches you some really fun facts. I'll sketch some of them in a little bit. So what we're seeing from all these connections with string theory from the Zamolodchikov formula is that generically deforming a CFT with TT bar is giving you a theory with a Hagedorn density of states. It's not a local quantum field theory, and the deformed classical actions already look stringy. This thing already looks like the action of a brain theory. So all of this is hinting that this is a new kind of structure. It's a new kind of structure somewhere between local quantum field theory and a fully fledged string theory. It's not completely clear what it is at this point. So the fun part about this story is that it's very much the right way to think about this is very much up in the air. We don't know yet. For example, basic questions like what the observables of the theory should be are very unclear. We have these energies. That's one set of observables you can play with. I'm not discussing at all the S matrix, but the S matrix is something else you can robustly understand. But are there correlation functions of local operators? Some people say yes, some people say no. Are there correlation functions of operators in momentum space? Some people say yes, some people say no. So it's all up in the air a little bit. But it's very, very intriguing. It's fun to be in a thing that is new. Let me make some comments about supersymmetry. These TT bar deformed theories also have the magical property that if your original theory was supersymmetric, the deformed theory is also supersymmetric with the same amount of supersymmetry. And an intuitive way of seeing that is supersymmetry implies some degeneracy in the spectrum. You have some bosonic state with some energy, you get some fermionic state with the same energy. And the energy formula preserves that degeneracy because it only depends on the initial energy. So those degeneracies get preserved along the flow. And so each of the symmetries should be preserved along the flow. This is weird. It's particularly weird when you think about a maximally supersymmetric theory, because those are rare to construct. And the fact that you can generate them this way is surprising to me. In fact, you can make TT bar manifestly supersymmetric by modifying its definition slightly and writing it in terms of superfields. And we being this collection of these groups, you could replace TT bar by something that we call supercurrent squared, which is an expression written in terms of superfields. So it's manifestly supersymmetric. And you can write down an analogous flow equation in superspace. I've written it out here just schematically in 1-1 superspace. It's some combination of these supercurrent squared operators. And on shell, this is equivalent to TT bar, which means that it's both well-defined quantum mechanically, and we'll get back to the same energy formula, but with supersymmetry made manifest. So there is a very beautiful interplay here between supersymmetry and TT bar, which we can use to our benefit to try and learn more about what's going on. It also is a great way to figure out how TT bar should come into string theory, because maximally supersymmetric structures that are compatible with all the symmetries in string theory should just be generated quantum mechanically. There's no reason for them not to be there. And if there's no reason for them not to be there, they should be there. And we'll see some analog, some version of that in a moment. We can also use TT bar at the classical level. And here we're not worrying about the quantum definition as an organizing principle. So, and we can go beyond 2 dimensions for this discussion. For example, in 4 dimensions, if you considered the 4-dimensional stress tensor, and you consider T mu nu, again, quadratic in the stress tensor, minus this trace square term with a 1/2, well, we don't know whether this operator exists quantum mechanically. It should be, in principle, dependent on the ultraviolet theory. But we can still study the classical flow. And Conti and collaborators took exactly this combination for free Maxwell theory in 4 dimensions, and they solved the flow equation. And lo and behold, what came out of the flow equation is the very famous Born-Infeld action, square root of the determinant of eta plus f. So this nonlinear theory of electrodynamics emerges as the solution to a TT bar-like flow equation in high dimensions. There is no obvious reason that had to be true that I know of, but it gives you a very different way of thinking about Born-Infeld itself. And again, this almost certainly does not extend to a quantum theory. So there's no good reason yet to believe that this is a quantum theory, as opposed to the 2-dimensional case where we have good reasons to think there is a quantum theory. Similarly, you could consider a supersymmetric theory in 4 dimensions, which possesses a Ferrara-Zurino multiplet, so some multiplet of currents, including a supercurrent. And in this case, we proposed, again, a supercurrent squared operator, which the details of which are not critical for us, but it took this form. And if you expanded this thing out, you would get the T mu nu minus a 1/2 trace T squared term, but you get additional contributions, which are not trivial. I mean, there are critical additional contributions, but you could solve this flow equation starting with supersymmetric Maxwell theory, given by a field strength superfield W alpha with an action that's this F term D2 theta W squared. And if you solve the flow equation, lo and behold, you find a fairly involved expression, which happens to be the expression for super DBI. So, and super DBI with, So this structure, even classically, is giving us a very different way of thinking about actions that we know and have studied in the past, like Born-Infeld, which play a very prominent role in brain physics.
Sorry, Simon,
Sorry, go ahead.
Did we just so somehow for the classical d equals 4 n equals 1 stuff, are you still using anything about conformal or scale invariance, or this is just?
No. Oh, very good. I should have emphasized this point more. So TT bar in 2 dimensions does not require the initial theory to be conformally invariant. It could be massive. it doesn't have to be conformally varied.
But if it was conformal, then you can get that nice closed form for the energy spectrum of the deformed.
Exactly. That's the big plus of conformal invariance, that you can write down a closed form expression.
Mhm.
In fact, I don't remember seeing a closed form expression even for the massive boson. Otherwise, I think we played with it for a bit, but it got shuffled to one side at some point. So I think the cases people really focus on are the cases where you can just apply that formula, because you've got a nice solution right away. Very good. I'm going to make one more comment along these lines. So I might be misleading you into thinking that you take any nice theory, like say Yang-Mills in 2 dimensions, and you TT bar deform it, and you're going to get the Born-Infeld action out. But that really could never have been the case, because TT bar is really the stress tensor of the theory times the stress tensor of the theory is quadratic. But the stress tensor of the theory would involve a trace, say over the Yang-Mills degrees of freedom, something morally trace f squared, trace f squared. So it would be a double trace operator. And Born-Infeld itself only involves single trace operators. So Born-Infeld itself is trace of f to the 4th, for example, as opposed to trace f squared, trace f squared. So TT bar is really a double trace definition. So when you go ahead and deform d equal to Yang-Mills, you actually find a fairly complicated expression in terms of some hypergeometric. But one you can study explicitly. And for example, actually one of our graduate students, Aurora Ireland, and her collaborator, wrote a nice paper on this stuff. But pure Yang-Mills in 2 dimensions is topological. It has no propagating gluons, it has no propagating degrees of freedom. So this is a setting where one might say, well, you took a theory that was topological, you deformed it, get some action, you've got some different weighting of the topological theory. On the other hand, you could do the same thing by taking the gauge theory and coupling it to charged matter. For example, I know Jock, for example, spent a lot of time thinking about GLSMs. You could take your favorite 2,2 GLSM in 2 dimensions and deform it by TT bar and ask what happens. And there, of course, there are physical degrees of freedom. All the charged matter is dynamical. So if you take a seed theory, which is, say, Yang-Mills plus some charged scalar, and we could replace this with a more complex theory if you want, something with maximal supersymmetry, for example, theory on a D string. You can write down a PDE for the deformed Lagrangian by computing T mu nu lambda along the flow, and then you can solve it. And the solution is involved and can be solved in various ways, either as a series solution in lambda, or in terms of some implicit definition, in terms of an integral expression, or, and this is the way I'll sketch here, by dualizing the gauge field to a scalar and giving a closed form Lagrangian in the dual variable. Let me just show you that. So in that third case, we replace the f mu nu square term with f mu nu coupled to a scalar chi, and just add a quadratic chi-squared term. So if you integrated this chi out, you'd be back at the starting point of f mu nu squared plus a charged scalar. But here we can actually work out the form of the Lagrangian in terms of chi. And there's an expression that relates chi to the electric field and to d phi, which can be inverted order by order in lambda to solve for the resulting Lagrangian in terms of physical fields. It's kind of interesting, you can actually do it in this case. And I just brought out the expression here to order lambda to the 4th. And leading order is f squared. Then there's this lambda f to the 4th, and there are various coefficients for these higher order terms. We can compare this against the standard Born-Infeld expansion, which is square root of 1 plus 4 lambda f squared. The sign here looks like a plus because this f squared is minus the electric field squared. And I'll plug that back in a moment. But you can see that by comparison, the coefficients are different. So even the abelian theory is different here. So it's weird. I did not guess such a thing, and maybe I should have guessed based on some facts from string theory that I'd forgotten about. But I had always thought that there was a unique, maximally supersymmetric combination of f to the 4th, f to the 6th, f to the 8th that came out of that resummed to give you Born-Enfeld. But this is also a maximally supersymmetric combination of f to the 4th, f to the 6th, f to the 8th that does not resum to give you Born-Enfeld. It resums to give you this hypergeometric. And this is actually, I think, a subleading loop correction to the Born-Enfeld action on a D-brane. One of the striking characteristics of the nonlinear electrodynamics that's Born-Enfeld is, and here I'm plugging in the electric field, the physical electric field, so there's a minus sign now, is that there's a critical value for the electric field. If you try and make it too large, this square root will again go imaginary. So the electric field, so that reality condition forces the electric field to be less than 1/√8 lambda. Now, this theory, this deformed non-abelian theory has some really interesting properties. Because it's a TT bar flow, the theory should exist quantum mechanically. That's what we sort of expect. But unlike DBI, it is well defined even for a non-abelian theory. There is no well-defined notion of non-abelian DBI. Basically because in the non-abelian case, commutators, the commutator of two covariant derivatives is a field strength. And that means you can't ignore things like covariant derivatives acting on field strengths, unlike abelian DBI, where there's a notion that little d mu of a field strength is an acceleration term that you can throw away. Here TT bar is giving you a non-abelian answer, which is kind of neat. It's again compatible with maximal SUSY, which means it should appear on a D string, for example, this set of couplings. I would love to see that come out of string theory. There's some kind of disk plus handle computation. There's basically a loop correction to the beta function argument, I think, that gives you Born-Enfeld that should work in this case, maybe. But as we saw, it differs from DBI even in the abelian case. In this case, you can check that there's also a critical electric field, but the value is different. So the electric field has to be less than square root of 27 over 512 lambda. So some value, but the value that is different from Born-Enfeld. And again, we expect this action and high dimensional versions of it to appear as double trace corrections to Born-Enfeld and string perturbation theory. If we could do this from string perturbation theory, we'll have a natural generalization to high dimensions by looking at such corrections on branes beyond D strings, like D2 branes, D3 branes, and so on. Okay, this brings us to the final part of the talk, which is holography. I've got about 12 minutes, I think, roughly. Okay. Good.
Like so maybe 15 or something.
Okay, that'll be great, because yeah, then I can do it in a slightly more relaxed way. Good. So I'm going to sketch the most recent work we've been doing on this. Actually, I shouldn't say recent. This project is probably 1.5 years old, but COVID plus a baby has delayed its appearance until hopefully next week, to the detriment of my student and former student. But I take all blame for that. So the idea is to explore and extend this holographic correspondence, case 2, proposed by Gideon, Itzhaki, and Kudasov. And the idea is to not worry about Wall Street string theory, but study it directly from a gravity perspective and see what we can get out. For example, a striking result would be if we could somehow get out the square root formula that characterizes these TT bar deformed theories directly from gravity. So let me step back for a second and take us back to 1997, a long time back. Around that time, the first version of holography that was exciting had emerged, which was called BFSS matrix theory. It was a discrete Lycombe quantization of M theory. given in terms of a matrix model that was the quantum mechanics of these zero branes. In that context, as people try to push up that holographic correspondence to higher dimensions, Seiberg proposed a version of holography, which is quite different from ADS-CFT. It's a holography that's supposed to exist in 6 dimensions. And the idea goes as follows. If you consider NS fibranes in string theory, so those are solitons in string theory that are very heavy or weak coupling, and you take Q5 of those NS fibranes, they have a metric that was written down long ago by Callan, Harvey, Strominger, maybe Giddings. So there's directions along the fibrane, the 5 plus 1 dimensional wall volume, which in string frame is just flat. It's just a flat metric. And there's a set of transverse directions, 4 transverse directions to the brain, which lives in 10 dimensions. And what comes along with this metric is a dilaton, which has some asymptotic value G string and this radial dependence as you move away from the brain. As you approach the brain, you can see that the brain is located here at r equals 0. So as you approach the brain, the dilaton is blowing up. So this is a solitonic solution of string theory where the dilaton asymptotes at infinity, at r equals infinity to some constant value, G string here. And as you approach the brain, it blows up to infinity. And associated to this dilaton is an H field. We won't have to worry about the H field much. It's critical, but it's coming along for the right. So what Seiberg proposed was, let's take a limit where we scale this asymptotic value of G string to 0, keeping fixed alpha prime, or the string scale, and simultaneously rescaling the radial coordinate. If you do that, you end up with a gravity background, which is much simpler. It's still got the flat string metric along the brain. Nothing's changed along those 6 dimensions. But the transverse metric to the brain is now a flat metric, dr squared, plus a 3 sphere of fixed size. It doesn't vary. And the dilaton has simplified to a simple linear dependence in this coordinate, R, the radial coordinate to the brain. That's why this thing is called a linear dilaton background.
Is R positive after doing this redefinition?
R is positive. So R as R goes to infinity, this e to the 2 pi will go to 0.
Yeah.
Because it'll go like e to the minus r.
Yeah.
So asymptotically, we want it to vanish. And as you approach the brain, as you approach, I guess, I see. Yeah, good. Yeah, R is probably running from, it shouldn't be 0 to infinity. It should still blow up as you approach the brain. So maybe plus infinity to minus infinity here, in some suitable limit. So the nice thing about this decoupled theory is that you have an exact Walsh conformal field theory description. So it's just flat for R51. There's nothing happening there. You've got an SU2 WZW at level Q5 for this S3 with H flux. That's known theory. And then you've got this direction, which is determining the dilaton. So the dilaton, the coupling itself will just change in that direction. And the dual to this gravity background was dubbed little string theory, because it's supposed to be a theory that is non-gravitational. So it's not like a full string theory that has a spin-2 graviton. But unlike the ADS-CFT correspondence, where this little string theory would be replaced by a CFT, it has a physical scale. It has an M string, a mass scale set by 1 over root alpha prime. That's held fixed. So this is not a conformal field theory. It's something else. And in fact, we ran into the difficulty back then, those of us thinking about this story, that we just didn't know how to define little string theory intrinsically. It was some kind of weird theory that generalizes quantum field theory. Kind of sounds familiar from the intro of the talk. But in '97, it was like, well, we don't really know many examples of that type. And also the other difficulty was the Walsh theory became strongly coupled as you approach the brains. So what we do know is that this is not a local quantum field theory, Although if you took the low energy limit, you took that string scale m string to infinity or alpha prime to 0, it could be a CFT at low energies. But we also know from some work of Kudasov and Sahakian that the theory has a Hagedorn density of high energy states with a Hagedorn temperature set by, again, the string scale and the square root of Q5. So sounds kind of like the features we saw from TT bar at the beginning. And so that really is the source of all the excitement about this to me, that this theory that was sitting there in 6 dimensions, whose existence we knew, but whose properties we couldn't really say much about, may now be, we may now be in a position where we can say more, where we can actually connect this to a deformation by an irrelevant operator like TT bar. It won't be precisely TT bar, but it'll be something like it. All right, to make this connection, we need to modify that 6-dimensional setup. So to that 6-dimensional collection of fibranes, these Q5 NS fibranes, we'll add some fundamental strings, Q1 fundamental strings. There's a metric that describes the collection of branes. The only things I want to note about this metric are there's some harmonic functions that go like 1 and R squared that appear in the solution. They have coefficients R1 and R5 that are basically proportional to Q1 and Q5, the amount of charge. These are just sources, and in those sources are Q1 and Q5. There is a three-dimensional spacetime that will emerge, parameterized by time, the radial coordinate R, and an angular coordinate x5, a periodically identified coordinate x5. So there's a cylinder here, cross a radius, if you wish. And that three-dimensional spacetime is very important for us. Maldacena took a decoupling limit of that collection of branes. His decoupling limit was the one we just described, G string going to 0, but he also took alpha prime to 0. And in the combined limit, you end up with a solution that is ADS3, cross a 3 sphere, cross a 4 torus. And two funny things happen. Well, it's not funny, but there are two notable things happen. The string coupling is given by the ratio of Q5 to Q1. So taking a lot of fundamental strings makes the theory weakly coupled. And the length scale of this ADS space is given by square root of that string length times Q5. So taking a lot of fibranes makes the ADS weakly curved. This is one of the classically studied examples of ADS CFT, but this is in the frame where all the fluxes are NS. So there is a wall sheet description. There's no Ramon flux in the story. So strings on ADS3 are described by a WZW model on a group manifold. This ADS3 is SL2R. It has a symmetry group, which is the left-right action of SL2R at level Q5. And what Kudasov and collaborators studied was the Ramon sector of the theory, which in spacetime corresponds not to global ADS, which would be the vacuum, but to the 0 mass BTZ sector. Gravity in 3 dimensions, in 3-dimensional anti-de Sitter space is peculiar because you can have negative mass, which you can't have in high dimensions by the positive mass theorem. But the vacuum in ADS3 has negative energy, and that negative energy exactly matches the negative energy of the CFT vacuum that it's supposed to be dual to. But they didn't study that sector. In fact, instead, they studied the sector that has 0 energy, this m equals 0 BTZ, and in that sector, you can take currents from this SL2R left, SL2R right, and construct a current deformation of the wall sheet theory. So this is a marginal deformation of the wall sheet theory that you could just turn on. And when you turn on this deformation of the wall sheet theory, you can check that what it should correspond to is turning on an irrelevant deformation of the holographic dual. What was the CFT that was supposed to be dual to it? And an irrelevant deformation that has dimension 2, 2. So there was this very beautiful connection of a marginal deformation of your world sheet string theory mapping to an irrelevant deformation of the CFT. And then along came Zamolodchikov. So this was an old fact. And then along came Zamolodchikov, and I think David realized, oh, this thing is probably got something to do with TT bar. And indeed, we can think of this d of x as something like a single trace version of TT bar if you compute its effect on the spectrum, meaning you compute it from this side. You can actually solve for the energy levels as a function of this marginal deformation in the world sheet, and you find the same square root formula for the energies of long strings in this m equals 0 BTZ sector. Extremely suggestive. You're seeing a lot of evidence that these two things should be related to each other, but there's some peculiarities too. The CFT that's supposed to describe this theory is not believed to be a symmetric product. The only case that it might be a symmetric product is the case of one fibrate. And that's been studied recently quite heavily by Gabadiel, Gopal Kumar, and Gabadiel students like Eberhard and Day and friends, who very extensively tried to reconstruct a symmetric product, and quite successfully tried to reconstruct a symmetric product in this particular case from the world sheet string theory. In every case with Q5 greater than 1, this cannot be the case. There has to be something else beyond the symmetric product. But the only case where we could describe a single trace version of TT bar was that symmetric product, which is why this D is something like single trace TT bar, but it can't be precisely single trace TT bar. It must be something else closely related. And we don't know what it is today. So it's sort of experimental data that's being thrown out here. Okay, this is just a review of things that Kudasov and collaborators have studied and understood. So let's leave the world sheet and turn to geometry in the final minutes of the talk. We can ask the question, could we compute the mass of black holes in a space-time deformed like this directly from gravity? So the first thing is we have to write down metrics for black holes with some mass and some spin. And for this purpose, we can just ignore the S3 and the T4. Everything's happening in three-dimensional gravity. The S3 and T4 are there, but they're not going to play any significant role. Let's also set the spin to 0 to make our life simpler. So we're just going to look at a non-spinning BTZ black hole initially. What characterizes this geometry is that as you go out to infinity, it's not asymptotically ADS, but instead it's asymptotically linear dilaton. We have this linear dilaton turned on, and it's becoming a linear dilaton theory. You can work out, using the symmetries and some analysis, you can work out the form of solutions that go from BTZ in the interior to the right asymptotics near infinity. And we don't have to worry too much about any of these parameters. I'll just highlight some features of the form of the solutions. We have to put these in a clearer form, I think. But I have a suggestive deformation parameter lambda here, which will be the lambda of the dual theory at the end. And then this RE squared is basically minus the mass. And R1 squared was proportional to Q1. And R5 squared is proportional to Q5. So there's some parameters here. Let me contrast this with a better known solution for just BTZ, which has this form. And I should put them on the same page, actually. Now I think that would have been easier to contrast. This is basically, when lambda goes to 0, this will go over to BTZ with mass m. But it has different asymptotics as you go out to radial infinity. Okay, one last ingredient. We're almost there. We need a way of computing mass in this spacetime. And there is a beautiful formalism that Ayer and Wald constructed called the covariant phase space formalism, which can be used to precisely answer this question. Namely, given a spacetime, I mean, what's nice about this formalism is, unlike the ADM mass or other definitions of mass in GR, this one works sort of in a background independent fashion. For us, it's basically a black box that if you have asymptotic killing vectors that correspond to symmetries and a family of solutions, say labeled by mass or labeled by mass and spin, you can work out a charge associated to each killing vector. So for the asymptotic killing vector associated to time translations here, you can use that to compute the mass of the space-time, and there are contributions coming from the graviton, and there are contributions coming from the dilaton and the flux. The flux actually turns out to vanish in this case, but certainly the graviton and dilaton both contribute. It's a little bit of an involved calculation, but at the end, you get a charge, which should be the mass of the space-time, which can be expressed in terms of the parameters of the solution, but we can re-express those parameters in terms of just mass of the BTZ in the interior and the deformation parameter lambda, and it has this form. Surprisingly, you get this square root. You get a square root of 1 plus lambda times this mass minus 1. And if I contrast this with what we expect from the usual double trace TT bar, with a momentum set to 0, because we have no spin. Momentum maps to spin in this dictionary. They have the same form. So it seems as if gravity in asymptotically linear dilaton backgrounds could have told you about the TT bar energy formula without knowing about TT bar. I mean, that's really what it looks like here. So we seem to have a match. And the match brings up lots of interesting issues and puzzles. This mass is positive for black holes with m equals 0 or greater, but global ADS sits in there with a negative mass. That's what would have corresponded to the CFT ground state. And here it's saying that global ADS has to become unstable if we make this lambda too big, just in GR. I've actually never, I'm sure this happens in other contexts. I haven't seen it before, where the vacuum will become unstable in GR in some setting. We believe, so we have a family of solutions that actually take us from the fully undecoupled theory to the asymptotically linear dilaton theory to the ADS theory. So we can sort of take limits. And from looking at those limits, we think that this instability of the ground state in string theory corresponds to a closed string tachyon emerging. If the closed string tachyon emerges in the brane configuration, you'd have to take it into account in trying to understand decoupling limits. And it presumably takes you somewhere else from this solution when it condenses. But we don't have much more to say about it than that at the moment. We can extend this to the spinning case. It's actually quite non-trivial. There's some issues of non-integrability of the charges that have to be sorted out. And the nice thing about this entire formalism from gravity is we can move away from just NS flux. So in ADS-CFT of conventional type, of this type, if you changed from NS fibranes to PQ fibranes and PQ strings, it's not super exciting. All you've done is change the value of your string coupling, and you've changed some of the parameters in the theory, but you could dualize to a frame where you're weakly coupled here. As soon as you turn on this linear dilaton deformation, you can't do that. So now you can actually have different theories that asymptote not to little string theory, but to the kind of little string theory found on PQ fibranes. So there's something we're going to learn, I think, about field theory deformations from this. And this is something that Chris and I are going to hopefully write up once this thing comes out. And let me close by saying we're getting our first glimpse of what lies beyond ADS-CFT. And hopefully there's going to be much more to learn about holography in spacetimes that are more general from this story. Thank you for your patience.
Thanks very much, Sab. That was beautiful. Any questions?
Who's still awake?
Well, you're still awake. That's the main thing. Yeah, not much is known about the theories on PQ fibranes, as far as I understand.
there's something weird and interesting about them, because sorry, if you just study D1 D5 in the purely Raman sector and try to do this deformation, it fails. You really need to have some NS charge with a fibrine in the background. But once you have some NS charge with a fibrine in the background, there's a different kind of decoupling. Once you take the decoupling limit, you can't dualize the PQ fibrine back to a pure NS fibrine state. You get frozen there. So that's a situation where from the interior, you thought you might be able to do an S duality, make it all look like NS again, but you're stuck by that decoupling limit. Right. So it actually changes qualitatively the nature of the correspondence. So what this suggests is that there's other kinds of like PQ translates of TT bar in the field theory. It's the same field theory in the interior at just with different values of the charge. So you have some CFT2 that depends on Q1 and Q5. For different values, it's weakly coupled in different duality frames. So for some value, it's weakly coupled in the Raman frame, for some other value in the NS frame, and for some other value in the PQ frame. And normally you would just dualize to the right frame. You don't think twice about it, where it's weakly coupled. But here you can't do that, because as soon as you've turned on this deformation, you're no longer free to dualize without destroying the asymptotics of your spacetime. So I think it's going to give us more examples of holography of this type. But what it's really suggesting is that there should have been some action on TT bar that would have taken you to another ultraviolet theory like TT bar, but different. Yeah, I think there's going to be something to be learned from this.
And the closer.
There's a lot.
Sorry.
Go ahead.
Yeah. So, is there a way to test for the tachyon? Is there a calculation you can do that would sort of be a smoking gun type thing?
Yeah. If we don't decouple at all, we just take the full solution with all the parameters in it, then there's a winding string. Asymptotically, it becomes just a circle that's flat. And then there's a winding string that will become tachyonic that we can see. And the question is then tracking what happens to it when you at least decouple to the asymptotically linear dilaton story, without going all the way down to ADS, but going into this. Could one see what's happened to that tachyon, and what could happen when it condenses? That's a much harder question. Where does it take you? There's some lower energy configuration somewhere. I mean, the tachyon is telling us basically, or even the energy going imaginary is telling us that there's some lower energy configuration that we should see. So maybe there's a phase transition in the gravity theory that takes us somewhere. But yeah, I don't know what it does at the moment. I think some of the directions here that really are interesting to me is just the classical geometry of the space-time and how is it encoding information holographically. Because all those questions in AES are extremely interesting in connection with quantum information and quantum error correction. And this is going to be something related but different.
Right.
So where that story will go is very unclear at the moment, but it looks kind of intriguing.
Yeah.
In terms of understanding what's happening.
It's definitely good to go beyond ADS.
So can I ask you a couple of trivial questions?
Yeah, I'm sure they won't be trivial, but go right ahead.
Do you hear me from here?
Yeah.
Yeah.
So it's great.
Hey.
Well, first of all, the solutions that you found, they are in pure 3D gravity with a cosmological constant? Or?
They're in pure 3D gravity with a dilaton.
I might have okay, with the dilaton and I guess you also have
the
boxes.
B field.
And the B field. But you didn't search for the solution in full 2D supergravity, or I couldn't understand that.
I couldn't quite catch the last thing. Actually, I think the sound was better the other way.
So the solutions are not embedded in a 10D Sugra calculation, right?
Ah, I see. It back reacted.
Yeah.
Do you want to try and get off? Yeah. Yes, sorry, a very bad setup. I think you should hear now. Do you?
Yeah, that's
Yeah.
good.
Yeah,
Right.
yeah.
Yes, I was just wondering whether this solution you can uplift to full 10D, because it seems like you didn't search for the solution, a solutions of type.
Oh no, very good, very good. So I didn't
Because
listen
you might
here, but-
search for like a role of supersymmetry in these solutions as well, right? If you uplift to a full.
Yeah. No, we actually did solve the full 10D equations.
All right.
We just didn't. I just didn't want to write out the solutions here. But we actually have the solutions for the full 10D theory. So it's not just restricted to the 3D setting. But the S3 and the T4 are typically not doing anything in the solutions. They kind of come along to the right.
So do you have any supersymmetry in these solutions, or?
It will depend on the sector. So for example, global ADS will have broken supersymmetry, but M = 0 will be supersymmetric. Positive M, yeah, there could be there should be some BPS ones. Yeah, you're right. There should be BPS ones too. But I think we didn't constrain them according to Susie. Maybe one should at some point.
The second thing I wanted to ask you is, so it looked like you studied also the rotating black holes with J non-zero, right?
Yeah.
So in that case, you have more freedom for the deformation. Can you see something like JT bar deformations or some other type of deformation?
Oh, very good. Very good. Good. We didn't do that here, but Wei Song and collaborators used an approach from TST to try to generate similar looking solutions, not from directly studying the gravity theory, but using the duality maps. And I think they looked at things with JT turned on. There is no in principle reason why one can't do JT this way. Though we didn't to TT bar. It was involved enough with TT bar that we didn't focus on that day. But that would be very interesting to study the JT case and see what they look like. I mean, presumably you need JT plus TT bar in the right combination to avoid closed time-like curves in space-time. I think JT bar on its own is probably going to be pathological as a gravity solution.
Can I have ask a question? Can you hear me?
Hi.
Yes.
Yeah.
Thank you for your talk. I enjoyed. I'm a mathematician, so I probably I understand every sentence, but wouldn't be able to comprehend if put them together. But it's probably you would understand. But my question is purely from a mathematical point of view. So to me, if whatever the physics did, mathematicians look at the solutions, right? The solutions of either from first principle or classical equations of motions, and the mathematician put a solution together, what we call the modular space. Whatever physics calculate, spectrum, partition functions, all these, we view it as certain information by look at have a mathematical definition on the classical modular space. And it's kind of like a limit. So from this, my limited, with understanding in this subject, so this is the first time I heard of these TT bar operators and TT bar flow. Can you explain to me? Just like a maybe very naive mathematicians try to understand the physics talk. Can you explain to me what this TT bar operator and the TT bar flow do to the classical modular space or whatever the equation has?
Yeah. That's a great question. So if you were starting, for example, with a conformal field theory or a family of conformal field theories within a moduli space, once you've deformed, the theory is no longer conformal. Yet you could have deformed at any point on the moduli space, and you would have gotten something. So it's unclear what one means by moduli space anymore in that setting. And even that statement is not completely true. You can obstruct. You can have moduli that you could have directions in your moduli space that could become obstructed. Not necessarily by TT bar, but by things like the single trace TT bar, where once you turn it on, you're no longer free to deform in those directions. Yeah, there's an interesting question about what the interplay with mathematics will be from this. I wouldn't be surprised if there is an interesting interplay, but probably, if I had to guess, it would be from studying variants of elliptic genera of some of these 2-2 theories, which the most basic invariants don't flow with this deformation, but there are some more exotic ones that look like they should flow. And if they flow, they'll flow to something that presumably will be modular. It may not be holomorphic anymore, but it will be naturally connected to a holomorphic object.
Great.
That's one direction that where there's an interesting math that might emerge. I'm not sure that answers the
no, that's perfectly answered. That's making me very happy because you can elliptic genera something. Like I was just intrigued by TT deformation of Susi and something which is I couldn't see where this deformation lead to. And now probably this would be an interesting thing too. Okay.
Yeah, I mean, I think the most basic invariants that get counted tend not to flow because they tend to involve just BPS objects. But I think if you arrange it right, you can make some of the energies flow on one side, and then you can ask what's happening in the story. Actually, even the partition functions themselves, which are non-holomorphic modular invariants, get deformed in an interesting way, and even for the free boson, that's already a non-trivial statement. So it's possible there's some interesting math lurking around here too.
Thank you. I think that's enough for me. Thank you. Thank you very much.
Okay.
Sorry, I just realized I was muted. Any other questions or comments?
Perhaps you could, it's something I'm not sure I got. You said at the beginning that TT bar was in maybe the Yang-Mills setting was equal to determinant, whereas normal term in the action is the norm squared of the Yang-Mills field. You said it was there was a determinant.
Yeah, good.
TT bar was, and so it's determinant of the over the internal indices, what you called A indices, I guess. Is that right?
Yeah, so let's bring this, whoops, all the way back to here. So TT bar itself is always determinant of the stress tensor. But the stress tensor
the stress tensor. So instead of the norm squared,
the stress tensor. So
determinant of the stress tensor.
Exactly. Yeah. Yeah, exactly. Determinant stress, and the stress tensor itself will be contractions of trace FF in an appropriate combination.
Yeah, sorry,
for the Yang-Mills case. So this will be some kind of fourth power in the field strength at leading order. That which will be double trace. It'll be sort of trace of some FF times trace of some FF, contracted appropriately.
It's freaking amazing when you think about it like that, that you can actually sort of solve, in some sense, this deformation, or, you know, integrate it up, because it's a very non-linear thing.
Yeah. Yeah, no, it's you know, it's weird, because as soon as you turn that thing on, then you deform the stress tensor again with higher order stuff, and then you flow up to get this action. But the fact that the answer is so pretty at the end in so many cases is surprising.
That's something very interesting.
Yeah, I mean, usually when structures like this emerge, which sort of touching on many areas of kind of theoretical physics, then there's likely to be a lot of deep physics lurking around here. So yeah. I mean, I should say, I've emphasized a very select set of points of interest in this topic. I mean, there's a lot of. I think if someone else was giving this talk, they would have given you a completely different set of reasons why this was interesting. With almost no connection to what I say. But that's another reason it's so interesting.
What's the different direction? It's really good.
Yeah, that's a lot of fun.
Yeah. Well, Sav, thanks very much for giving this talk, and for what it must be very early.
No, thank you for the patience.
Thank you.
So we'll give you the electronic clap.